Hello everyone and welcome back. My name is Mr. Koval, and in this video we're going to talk about how to use stoichiometry to find out the total pressure of gases in a container after the completion of a reaction. So let's get into this. So in this problem we're asked to consider the following reaction. We have C3H8 gas, which is propane, reacting with 5 moles of oxygen gas, and that's going to convert to or produce the carbon dioxide and water. This is carried out in a sealed, rigid container at 400 degrees Celsius. Initially, the reaction vessel is charged with 2 atmospheres of the propane, C3H8, and 12 atmospheres of oxygen. What will be the total pressure in the vessel after the reaction is complete? Okay, so you could either do this the easy way or the hard way. I prefer easy way. So one of the things you're going to keep in mind that you want to look for is if you're given atmospheres or volumes instead of moles, see if you can find that there's a proportionality between the moles of the substance and the atmospheres, the pressure, or the volume. And so you can then use, if there's a proportionality, you can then use the atmospheres, or you could use the pressure and or the volume as if it was like moles. So what do I mean by this? So one thing I want to point out is it's at 400 degrees Celsius. The reaction is happening at 400 degrees Celsius. So when you're producing your products, it's not as if the products and the reactants are in separate containers. It's all happening in the same container under the same conditions. So that means that the temperature here is held constant. They're not telling us of a change in temperature. So if they're not giving us a change in temperature, we can assume it's going to be held constant. But the fact that everything's happening in the same container, all of the gases are under the same conditions. So that means the volume of the container is not going to change and the temperature is not going to change. Why is the volume not going to change? Well, we're told that it's a sealed, rigid container. So if it's sealed and rigid, the volume's not going to change. So let's write that down. So volume and temperature are constant. Okay, so how does that help us? Well, if we're dealing with gases and we want to figure out what the relationship between the properties of the gases are, we can start with the combined gas law. And so remember, whenever you're trying to figure out what gas law to use and there's changes going on here, right? So you want to start with the combined gas law and then eliminate anything that's constant. So we have the combined gas law. So P1 V1 over T1 N1, where P is pressure, V is volume, T is temperature, and N is the amount of gas in moles. And that's going to be equal to P2 V2 over T2 N2. And so here's the combined gas law equation. So now what you do is you eliminate anything that's constant. So we know that volume and temperature is constant. So we're going to get rid of volume and temperature. So temperature is eliminated and volume is eliminated. And what does that leave? Whatever's left is the equation that we want to use. Okay, so here we have P1 over N1 is equal to, oops, I crossed out the wrong one. Volume should be canceled. And P2 over N2. So this is the equation. Now, we're not actually going to use this equation in the problem, but this tells us something. So the fact that I have P1 over N1 equals P2 over N2, what that tells me is that any change in pressure is proportional to a change in the amount. So if I double the pressure, then that's like doubling the amount of gas. If I half the pressure, then that's the same as having the amount of gas, right? So what does that tell us? It simply tells us that pressure is proportional to the amount of gas. Now, why is that helpful and useful? Well, in this case here, if pressure and the amount of gas are proportionally to each other, then we can use the atmospheres of that they give us for the reactants, and we can treat that as if they were moles, because the number of moles is proportional to the amount of pressure. So therefore, we can treat pressure as moles. So let's go ahead and do that. So here I have the equation. I'm going to go ahead and erase this to give myself some space. And so I have C3H8 plus 5O2 is going to give me 3CO2 plus 4 H2O. Okay, so here's my balanced equation, and we can do a stoichiometry table. So we can figure out what's going to be produced from what we're given. Now, we can do a stoichiometry table, like, so what do we start with? We could call it an ICF table. So I would be the initial amount that we're given, C is the change, and F is the final amount. Okay, so here we start with 2 atmospheres of the gas. So we can treat that like moles. So we have 2 atmospheres of the gas, of the propane, and we have 12 atmospheres of oxygen. So we're going to put 12.0 atmospheres under the oxygen. And we start with, this is before any reaction occurs. So just before the reaction occurs, we don't have any product. So we're going to put 0 for both of these. Okay, so this is the situation that we start with before the reaction. Well, now that we have to do the reaction, there's going to be a change. We're going to produce product, and we're going to lose reactant according to the mole ratios in the equation. So if we treat these like moles, then we can convert the amount of reactants we have to product. Okay, so how do we do that? Well, first we need to figure out what the limiting reagent is, because we're given a certain amount of both reactants. And one way to do that is to look at the ratio, right? So it's a 1-to-2 ratio here. So if I have 2 moles of my substance, or 2 atmospheres, let's say moles, right? If I have 2 moles of propane, well, how many moles would I need to react completely with the 2 moles, right? Well, it's 1-to-5 ratio. So if I have double the amount of the propane, then I need double the amount of the oxygen. So in this case, it would be 10, right? But I have 12. So I have more than enough, right? So I have an excess of oxygen, which means that I don't have enough propane to react completely with all of the oxygen. I only have enough to react with 10. So all of this is going to go away. This is my limiting reagent. So LR limiting reagent. Okay? So you can also do this by conversion factors, right? So I can take the amount of the propane I'm given and then use the mole ratio to find out how much oxygen is needed to react completely with that amount, right? So I can do, 2 atmospheres. And again, I'm treating pressure like moles because pressure and moles are proportional to to each other in this problem under these circumstances. So since the mole ratio is 1 to 5, that's going to be the same ratio for the pressure. So it's 1 to 5, so 1. So I'm going to put 1 atmosphere. Oh, I should have write the 2. This is going to be propane, so C3H8 atmospheres of C3H8 to 5 atmospheres of O2. So atmospheres of the propane cancel out. Now I have atmospheres of oxygen. So when I calculate this, I get 10 atmospheres of oxygen needed to react with 2 atmospheres of propane. So now I can kind of fill in the table. So then all of my propane is going to go away. So I'm going to use up 2 atmospheres of the propane. That 2 atmospheres is going to react with 10 atmospheres of oxygen. So I'm going to subtract out 10 atmospheres of oxygen because the 2 atmospheres of the propane reacts with 10 atmospheres. So I'm losing 10 atmospheres of oxygen and I'm losing 2 atmospheres of the propane, right? So what about my products? I'm going to produce products. So there's going to be, I have to use the mole ratio to figure out how much product is formed from the 2 atmospheres of the propane that is used up. Since this is my limiting reagent, the amount of product is going to depend on the limiting reagent. So since I lost 2 atmospheres of my propane and the mole ratio between propane and carbon dioxide is 1 to 3, then if I lose 2 moles or 2 atmospheres of the propane, then I'm going to gain 3 times as much in carbon dioxide. So 2 times 3 gives me 6. So I should get 6.0 atmospheres of carbon dioxide. And again, I can do a conversion factor using the mole ratio to help me out. So I can do that over here, or I can do it down here. So I have, again, 2 atmospheres. I'm going to start with 2 atmospheres of the propane, C3H8 over 1. And then I'm going to use the mole ratio between propane and carbon dioxide, 1 to 3. But I'm going to do atmospheres because atmospheres, the pressure is proportional to the moles. So I'm going to have 1 atmosphere of the propane on the bottom and 3 atmospheres of carbon dioxide on top. So 2 times 3 gives me 6.0 atmospheres of the carbon dioxide. And so that you can do it by doing conversion factors, or you can just kind of eyeball it and do it this way. The numbers here are easy enough where you can pretty much figure it out using the ratio. So if we do the same thing here, so I want to now do water. Well, how much water is produced? So again, it's 1 to 4 ratio. So here I have 2, so I'm losing 2 atmospheres. So for every 1 atmosphere I lose here, I gain 4 over here. So since I'm losing 2, that means it's 2 times 4, and I'm going to gain 8 atmospheres here. So now I filled that in, and now to find out the final amounts at the end of your reaction, you subtract the first row, you subtract the second row, the change from the first row. And so when we subtract this, or I shouldn't say subtract, I should add these together. So when I add these together, then I get the final amounts. So adding these together, I get 0. So I have no propane left over since that's the limiting reagent. So I add these together, subtracting 10 from 12. I end up with 2.0 atmospheres of oxygen. And add these together, of course, that's going to be 6.0 atmospheres of carbon dioxide. And add these together, get 8.0 atmospheres of water vapor. And so they're asking us what will be the total pressure in the vessel after the reaction is complete. So you just add these together, right? Or add these together, but 0, of course, doesn't do anything. So 0 plus 2 plus 6 plus 8, that's going to be equal to 16.0 atmospheres of pressure when the reaction is over. And that, ladies and gentlemen, is how you attack this sort of problem. I hope this was helpful. If you enjoyed this video, if you liked it, then please like the video, share the video, hit that like button over here somewhere. Also, make sure that you subscribe to my channel. Help me out here. Also, click that notification bell. When you do, make sure that you click all so you're notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. I would love to hear from you. If you have a problem you want me to go over, if you have a topic you want me to cover, put that down below. I would love to do that for you. Thanks for joining me, and have a great day.